The goal of the class today is to introduce what we have called the diastrait time, which is the mean first passage time of a Brownian particle to find a small target inside a cusp. So I would like now to introduce specifically the problem. So suppose we have a domain, and this domain is here represented. So this is a domain omega, and this is the absorbing part of the domain. So this is called d omega a, and inside such a domain we assume that there is a Brownian particle, and the particle has to find here this find this absorbing part. And so the question we will be interested in is how long it takes for this to happen. So the two circles that have drawn here, 1 and 2, are here to represent the local behavior of the domain, which are well approximated here by the radius of curvature of the two disks. So the question is, suppose we start by defining the Brownian motion of a particle with diffusion coefficient d. So this is the classical Brownian motion, which is the Wiener process. It's a Gaussian variable of mean 0 and variance 1. And d is the diffusion coefficient, suppose positive. And so the mean first passage time is defined as follows. So this is the first time t, such that the particle hits the boundary omega a, condition that it started at a position x inside the domain. So this is tau of x, and the classical mean first passage time equation, the MFPT for the expectation of tau of x, which we call u of x, is solution of the equation d Laplacian u of x equals -1, u equals 0 on the absorbing part, the omega a, and the other part of the boundary where there is no absorption, du dn, equals 0. And so the goal of this lecture is to show how we can solve equation 1 asymptotically in such a domain omega. So the difficulty, of course, is to resolve here the cusp, which is here enlarged, but you can imagine that when d omega a is very small, so when d omega a goes to 0, the mean first passage time here goes to infinity, and the precise behavior of the mean first passage time as the omega goes to 0 is what we are interested in. So now I would like to rescale the problem and consider that we have now the two oscillator disks are now of radius 1. So the domain is now scaled. So just by, for example, if we have here epsilon, which is the size of the small hole in the previous graph, now we scale everything such that epsilon becomes epsilon divided by the radius r, and we're assuming that the radius r is the same for both disks, such that now those disks are mapped into disks of radius 1, at least for the first one, which is in here. So we have now set of axes, the x-axis and the y-axis that we have here, centered here at the center of this disk. And so the difficulty to analyze this question is, of course, the cusp compared to the classical narrow escape problem that we have discussed in previous presentations. So to resolve the singularity, we are going to map the domain omega here using the conformal Mobius function, which is defined here so as omega of z, which is z minus alpha divided by 1 minus alpha z, where z is x plus y, x plus iy, and alpha is a parameter that we are going to choose equal to -1 minus square root of epsilon. And now the question is how the domain omega is mapped by this function. So what is w of omega? What it looks like? So for this, we are going to use the classical properties of conformal mapping. And so in this example, for example, the piece here, which I'm going to show in red. So what is the map of this? So we just need a parameterization, and the parameterization is z equals -1 minus x, where x basically goes from 0 to minus or to plus epsilon. And so, and this is this part is real, is on the real axis. So this belongs to this axis. And so since alpha is a real number, and this is z is on the x-axis, actually this piece here is going to be mapped inside here the domain, and this can be shown again. This I'm not going to show that precisely in this presentation. You just introduce this in the function and you calculate the image, and basically this has to be done for the 4 parts. That is, we have here the part of inside the x-axis. We have a second part which is along here the circle, and the third part here which is tangent, and then there is this outside part which is now in these dot lines. So let me show you the result of this mapping. So I'll start by redrawing the domain. So this is the circle, the tangent circles, and this is the absorbing part. So basically I would like to magnify this circle here. So let me do it. So this is the magnification of this circle. So 0 in here, the origin is exactly positioned at 0 in here, and this is the x-axis, and this is the y-axis. So the part here which is external, which is located at this position, will be mapped. Actually the point, what can be shown here is that omega of the point -1 is -1, so it's not moving. And so by definition of this inversion formula, of the inversion of the conformal Mobius function, what is outside the sphere is not inside the disk is not going to be located inside the disk. And since an ensemble that is located on the x-axis is also be located on the x-axis due to the continuity, the absorbing part of the boundary, the omega A, is going to be found in here. So this is the image. Again, I invite interested people to just do this calculation. So now the part here, which is along the circle, because the circle is invariant, will actually be located on this. I'll do it in blue, on a part here on the circle. And again, this can be shown by having a parameterization of the circle and injecting this into the conformal mapping. So this is for this part. So I'll draw with the color on the image, and then we have the green part, which is going to be this region. So this region actually is going to be found. The mapping of this region is a small region inside the an annulus, where the last part of the annulus corresponds to the black part here, which is going to be located at this on this line. So the entire domain is now mapped into a sub region, which is, so if this is of length epsilon, it turned out that this is of the order of square root epsilon. So the advantage of this transformation is that, as we are going to see in the equation, is that the Laplace equation is going to be transformed into a partial differential equation in this domain. And the partial differential equation, as we can see, as we are going to see, can be approximated as a one-dimensional. And this will reduce considerably the analysis. So Laplacian u equal -1 is now going to be transformed if we write the equation u of z equals v of w. So this is the in the z plane, and we have here what is called the w plane, where w is the variable of the mapping. So in the w plane we have this is the image of the domain omega. So the equation then for w can be derived from the classical properties of the Laplacian, which is Laplacian u of z is going to be w prime of z squared Laplacian of v for the variable w, where w prime is just the derivative of the conformal Mobius function, which is equal to here to 1 minus alpha square divided by 1 minus alpha z squared. And since this is equal to -1, we need to express this term in terms of w. So we have to invert the Mobius function, which is omega equals z minus alpha divided by 1 minus alpha z. So we have, so I'm not going to do all the calculation, but the result is that omega prime of z equals 1 minus omega plus square root of omega, so this is 1 squared divided by 4 omega, and this is squared. So here I have used that alpha equals minus 1 minus square root of epsilon. And I have neglected in this formula all terms that are in, so this is up to terms in O of square root of epsilon. So now we're actually ready to look at the equations in this new plane. So let's now rewrite the equation as omega Laplacian of v of omega equals minus, so there is also it's minus 1 divided by d, and then we have to use this omega prime of z squared. And let's study specifically this equation. So the equation is Laplacian v of omega equals minus 4 epsilon d divided by 1 minus omega plus square root of omega, and this is to power 4. Now, because the domain lies in this band of radius square root epsilon, we are going to neglect in first approximation all variation in R. So the Laplacian, instead of using the second order Laplacian in dimension 2, which is 1 over r d dv dr plus 1 over r square d dv d theta square, since we are almost on the disk of radius 1, we'll neglect all of this term and just get this ODE, and the variable theta here corresponds to the polar coordinate in this W plane, which is r exponential I theta, and r is approximated here as 1. So, and omega, so we have now d dv d theta square equals minus 4 epsilon d 1 divided by 1 minus exponential I theta plus square root of epsilon I theta to the power 4. So now we have to discuss the boundary condition that we are going to place on the domain. So for this, let me remind you that the absorption is here at the place where theta equals 0. So this, I'm sorry, theta equals pi. So which means that we have to use that v prime of the position pi here has to be equal to 0. Now, what is the boundary condition that we should position at this other extreme part of the domain? So first of all, a calculation, an analysis about the domain says that this limit angle here, theta limit, is actually of order square root epsilon. This can be a constant, so it's capital O of square root epsilon. Yeah, so, and this is not v prime, we have to erase this. This is not v prime here equals 0, but v of pi equals 0. So on the other hand, at theta L, we need to impose a reflecting boundary condition, which is v prime at a constant c square root epsilon equals 0. So now we are left, and this is what I will present in the next part of this talk. We are left with this ordinary differential equation that we have to derive, that we have to calculate. So dv d theta square is now a function of theta with these two boundary conditions, and the goal now is to solve this equation. So I'll break in here and resume for the second part of this diastrait calculation.